Hello, it's time to begin. Oh, I am monitoring my mic. Let's turn that off. I do not want to be listening to myself for the entirety of this stream. Alright, cool. So I'm going to be going through the third chapter of A First Course in String Theory by Barton Zweibach. I did the first two chapters in past streams. We're talking about the third one now. So this is going to be on electromagnetism and gravity in extra dimensions, which is going to be pretty neat. Also, I have been coughing all afternoon, so if my voice sounds weird, that's why. Alright, so I'm going to get started. So 3.1, Classical Electrodynamics. Unlike Newtonian mechanics, classical electrodynamics is a relativistic theory. In fact, Einstein was led by considerations of electrodynamics to formulate the special theory of relativity. Electrodynamics has a particularly elegant formulation in which the relativistic character of the theory is manifest. This relativistic formulation allows a natural extension of the theory to higher dimensions. Before we discuss the relativistic formulation, we must review Maxwell's equations. These equations describe the dynamics of electric and magnetic fields. Although most undergraduate and graduate courses in electrodynamics nowadays use the International System of Units, the SI units. Oh, is it not tracking my face? Okay, that was weird. The Heaviside-Lorentz system of units is far more convenient for discussions that involve relativity and extra dimensions. In this system of units, Maxwell's equations take the form, and then we have del cross E is equal to minus 1 over C, partial B over partial T, del dot B is equal to 0, del dot E is equal to rho, and del cross B is equal to 1 over C J plus 1 over C partial E partial T. So this is Heaviside-Lorentz units. I don't think I've used these units before, but I see what they're doing. So they chose specific units such that we don't have to keep in like all the factors of the permeativity of free space and the permeability of free space, epsilon naught and mu naught. So we just kind of got rid of those. The only thing that is giving any kind of scale here is going to be C, which I think makes sense if you're wanting to do a relativistic like formulation of everything, because this speed of light c is a direct effect of Einstein's theory of special relativity, like the finite value of the maximum speed, the speed limit for the universe. The above equations imply that E and B are measured with the same units. The first two equations are the source-free Maxwell equations. The second two involve sources. The charge density ρ with units of charge per unit volume, and the current density J with units of current per unit area. The Lorentz force law, which gives the rate of change of the relativistic momentum for a charged particle in an electromagnetic field, takes the form dp by dt. So the derivative of the 3 momentum with respect to time is equal to q times E plus V over C cross B. Since the magnetic field B is divergence-less, it can be written as the curl of a vector, the well-known vector potential A. So we have this definition here that B is the curl, so del cross some vector A. In electrostatics, the electric field E has 0 curl and is therefore written as minus the gradient of a scalar field, the well-known scalar potential phi. In electrodynamics, as equation 3.1 indicates, the curl of E is not always 0. Substituting 3.6 and 3.1, we find, into 3.1, we find a linear combination of E and of the time derivative of A that has 0 curl. So del cross E plus 1 over C partial A over partial T is equal to 0. The object inside the parentheses is set equal to minus the gradient of phi. So that's what they're setting. They're setting E plus 1 over C partial A over partial T. So they're setting that equal to the negative gradient of phi. And the electric field E can be written in terms of the scalar potential and the vector potential. So if we solve this above equation, we get that E is 1 over C, or minus 1 over C, partial A over partial T, minus the gradient of phi. While the potentials phi and A introduced above seem to just be auxiliary quantities used to represent electric and magnetic fields, we learn in quantum mechanics that, in fact, the potentials are more fundamental than the E and B fields. The Hamiltonian that describes the motion of a charged particle uses the potentials, not the fields. It is therefore relevant to examine possible ambiguities in the definition of the potentials. As we now show, the potentials associated with the set of E and B fields are not unique. If we change A into A prime, so A goes to A prime, which is equal to A plus the gradient of some field or function, epsilon, where epsilon is an arbitrary function of space and time, the new magnetic field B prime is equal to the old one. So we have B goes to B prime, which is del cross A prime, which is del cross A plus del cross epsilon, or del cross del epsilon. And this is the curl of a gradient, and this shows up a lot in like NM, like the curl of a gradient always goes to 0. So this vanishes and we're just left with del cross A, which is exactly the original magnetic field. So it is, the magnetic field goes to itself. So it's invariant under this transformation. These are what we call gauge transformations in ENM. Noting that the curl of the gradient is 0. Yeah, so what I just said. The change in A would not leave E unchanged, as it is clear from 3.8. We can repair this, however, by giving phi a change too. In fact, so we have to take phi goes to phi prime, which is equal to phi minus 1 over c partial epsilon partial t, and A goes to A prime, which is A plus del E. So we add on a gradient of a some function to the vector potential, and we subtract off 1 over c times the partial derivative with respect to time of that function from the scalar potential. Okay. Neither B nor E is changed. The changes of the potentials indicated above are called gauge transformations, and epsilon is the gauge parameter. Okay. Two sets of potentials phi A and phi prime A prime that are related by gauge transformations are physically equivalent. It follows that physically equivalent sets of potentials give identical electric and magnetic fields. It can happen, however, that potentials phi A and phi prime A prime give the same electric and magnetic fields, but still one cannot find an epsilon such that 3.10 holds. In such case, really, it's in such a case. In such case, the potentials are not gauge equivalent and must be considered physically different, even if their E and B fields are the same. The surprising situation can occur in spacetimes with compact spatial dimensions, and will feature in our later studies of D-branes in section 18.3. It does not happen in Minkowski space. In the presence of compact spatial dimensions, a related subtlety occurs. Given some E and B, there may not exist potentials phi and A that satisfy 3.6 and 3.8. We are and are well defined throughout the compact part of the space. The gauge transformations come to our help. It is not strictly necessary to have a uniquely defined potential phi and A all over the compact space. A set of potentials defined on patches that cover fully the compacted space is admissible, if in the regions of overlap between the two patches the corresponding potentials are related by gauge transformations. Okay, I think I need to think about that one for a second, kind of break that down. So it's saying that you don't necessarily have to have a gauge transformation that is valid for the entire manifold. You can have it where you have different potentials in different parts that are valid, they describe the electromagnetic fields on the regions where they exist, but only the overlap needs to have some transformation between the two. Okay. I'm hoping they bring up an example, because I'm having a hard time kind of visualizing what that would look like at the moment. All right. Given our statement that potentials, given our statement that potentials are not needed, in quantum mechanics, We must conclude that a configuration of E and B fields that does not arise from admissible patterns cannot be discussed. By the introduction of potentials, the source-free Maxwell equations 3.1 and 3.2 are automatically satisfied. Equations 3.3 and 3.4 contain additional information. They are used to derive phi and A. So we're going to start with now 3.2, electromagnetism in 3 dimensions. What is electromagnetism in 3 spacetime dimensions? One way to produce a theory of electromagnetism in 3 dimensions is to begin with 4-dimensional theory and eliminate one spatial coordinate. This procedure is called dimensional reduction. In 4 space-time dimensions, both electric and magnetic fields have 3 spatial components, Ex, Ey, Ez, Bx, By, and Bz, respectively. It may seem like that reduction to a world without the z-coordinate would require dropping the z component of the 2 fields. Surprisingly, this does not work. Yeah, I'm guessing we drop the x and y from the B field because it's a pseudo-vector. Maxwell's equations for the Lorentz force law make it impossible. In order to construct a consistent 3-dimensional theory, we must ensure that the dynamics does not depend on the z direction, the direction that we want to eliminate. If there is motion, it must remain restricted to the xy plane. It is thus natural to require that no quantity should have z dependence. This does not necessarily mean dropping quantities with a z index. Yeah, I think that's what I was saying. Like, we'll still have the bz component, but we won't have the bx or by components because those can give you like through your Lorentz force, give you forces in the z direction. All right. The Lorentz force law 3.5 is a useful guide to the construction of the lower dimensional theory. Suppose that there is no magnetic field. Then in order to keep the z component of the momentum equal to 0, we must have Ez equals 0. The z component of the electric field must go. The case of the magnetic field is more surprising. Assume that the electric field is 0 if the velocity of the particle is a vector in the xy plane. The component of the magnetic field in the plane would generate via the cross product a force in the z direction. On the other hand, the z component of the magnetic field would generate a force in the xy plane. Yep, that's... why does the face tracking keep going? Or am I just, like, being way too still? Okay. We conclude that bx and by must be set equal to 0, while we can keep bz. All in all, Ez equals bx equals by equals 0. The leftover fields Ex, By, and Bz can only depend on x and y. In the 3-dimensional world with coordinates t, x, and y, the z index of Bz is not a vector index. Therefore, in this reduced world, Bz behaves like a Lorentz scalar. More precisely, it is an object called a pseudoscalar. Okay, cool. I know what that is. All right. Something's going on with the... I need to... Alright, hopefully that'll fix things. Because Cal keeps going catatonic. Alright. In summary, we have a 2-dimensional vector E and a scalar field Bz. We can test the consistency of this truncation by taking a look at the x and y components of 3.1. So this gives us partial Ez over partial y minus partial Ey over partial z is equal to minus 1 over c partial bx over partial t, and partial Ex over partial z minus partial Ez over partial x is equal to minus 1 over c partial by over partial t. Okay. Since the right-hand sides are set to 0 by our truncation, the left-hand sides should vanish as well. Indeed, they do. Each term on the left-hand side in the left-hand sides equals 0, either because it contains an EZ or because it contains a Z derivative. You may examine the consistency of the remaining equations in problem 3.3. While setting up three-dimensional electrodynamics was not too difficult, it is much harder to guess what five-dimensional electrodynamics would be. As we will see next, the manifestly relativistic formulation of Maxwell's equations immediately gives the appropriate generalization to other dimensions. Okay, so now we're going to talk about 3.3, manifestly relativistic electrodynamics. In the relativistic formulation of Maxwell's equations, neither the electric field nor the magnetic field becomes part of a 4-vector. Rather, a 4-vector is obtained by combining the scalar potential phi and the vector potential A. And so what we call the vector 4 potential, A mu, which is phi in the 0 component, and then A1 in the 1 component, A2 and A3 and those components respectively. The corresponding object with down indices, so A mu is equal to minus phi, A1, A2, A3. So this is exactly what you would expect from just using the metric tensor to lower the index of this vector 4 potential. From A mu with a lower index, we create an object known as the electromagnetic field strength, F mu nu. And so that is F mu nu is equal to partial mu A nu minus partial nu A mu, where here the partial mu just means the partial derivative with respect to the x mu coordinate. Equation 3.15 implies that F mu nu is antisymmetric, so therefore F mu nu is equal to minus F nu mu. It follows from this property that all diagonal components of F mu nu vanish. So F00 is equal to F11 equals F22 equals F33, which all equals 0. Let us calculate a few entries of F mu nu. Let I denote the spatial index, that is, an index that can take the values 1, 2, or 3. Making use of 3.15 and 3.8, we find that F0i is equal to partial AI over partial x0, and remember that x0 is just the time coordinate, scaled by the speed of light. Partial a0 over partial xi, which we'll remember a0 is just the scalar potential phi. So this is going to be 1 over c partial a I over partial t plus partial phi over partial xi, which is minus e I. So the 0i components of the field strength tensor are the components of the electric field 3 vector. And similarly, we can calculate F12. So that's going to be partial 1 A2 minus partial 2 A1. So that's partial x AY minus partial y AX, which is just the z component of the magnetic field. And if we keep doing all of that, what we end up getting is that F mu nu can be written as a matrix where we have 0 on the diagonals, and we have minus EX, minus EY, and minus EZ on these components, EX, EY, and EZ on these ones, BZ here, minus BY here, BX here, minus BZ, BY, and then lastly, minus BX. And we can see the anti-symmetry here, right? If we took this matrix and we kind of like flipped it along, this diagonal here, you would get the same matrix, but all of the components would pick up a negative sign. And that's basically what it means for a 2 tensor to be anti-symmetric. We see that the electric and magnetic fields E and B are encoded in the field strength tensor F mu nu. The gauge transformations 3.10 discussed before can be nicely summarized with the index notation as A mu goes to A prime mu, which is equal to A mu plus partial mu epsilon. Because we can see, like, if we want to transform the scalar potential like we did before, we add on a time derivative of some function epsilon, and that's exactly what the zero component here is going to do. And if we want to change the vector potential, like the 3 vector potential, we add on a gradient, which is what the space components of this operator here are. I feel like I'm talking too fast. I tend to talk too fast when it's about physics. If anyone thinks I'm talking too fast, just let me know. All right. Since gauge transformations leave E and B fields invariant, the field strength F mu nu must be gauge invariant. Indeed, we readily verify that F mu nu goes to F prime mu nu, which is defined as partial mu A prime nu minus partial nu A prime mu. And then we can use our definition of the gauge transformation on the vector 4 potential to get partial mu A nu plus partial nu epsilon minus partial nu A mu plus partial mu epsilon. And so we can look, this term right here and this term right here give us the original field strength tensor F mu nu, and then we have plus partial mu epsilon minus partial mu epsilon. And because we can, when we're dealing in flat space-time, like nothing weird happening, we can just kind of swap around these derivatives. Then these two things are going to cancel out, and we're just left with F mu nu. So the field strength tensor is invariant under these gauge transformations. In the last step, we noted that partial derivatives commute. Yeah. Recall that the use of potentials to represent E and B automatically solves the source-free Maxwell equations, 3.1 and 3.2. How are these equations written in terms of the field strength F mu nu? They must be written so that they hold when 3.15 holds. Consider the following combination of field strengths. So we have T, maybe I'll go down another row. T lambda mu nu is defined as partial lambda F mu nu plus partial mu F nu lambda plus partial nu F lambda mu. I believe these are called the Bianchi identities. T mu nu vanishes identically on account of 3.15 because we have partial lambda times partial mu A nu minus partial nu A mu plus partial mu A lambda minus partial lambda A nu plus partial nu partial lambda A mu minus partial mu. Gosh, this is a long one. A lambda is equal to 0. And yeah, because we can see like we have partial lambda, partial mu, A nu, and here we have partial partial mu partial lambda a nu. Right here. Oh, what happened to Cal? VC face is being a little bit of a hassle right now. Cal got possessed and started trying to flee the screen. But yeah, so like this term cancels with this one. This term cancels with this one. Yeah. And then this term cancels with that one. So all of the... Yeah, what's happening to... What? Why is that happening? Is it when I look down? What's going on? Cal's trying to run away. All right. But we can see that all of these are going to go to 0. I'm going to check my VC face settings right now. Maybe should I turn up motion smoothing? Ooh, it just makes him feel like sluggish. Okay. Maybe decrease the movement range too. Yeah, okay. Hopefully that will fix things. We'll see. Time will tell. Okay. Yeah, so again, using the commutivity of the partial derivative. So commutivity just means that we can basically swap the order of them. Like partial mu, partial nu of, well, I guess I can't just put those by themselves. They have to be acting on something. But like, so if some like function f is equal to partial nu, partial mu of that function f. So that's what it means for like the derivatives to commute. Okay. So yeah, the vanishing of t lambda mu nu just means that, yeah, like this equals 0. So this is a set of differential equations for the field strength tensor. These equations are precisely the source-free Maxwell equations. To make this clear, the first note that t lambda mu nu satisfies the anti-symmetry conditions. So t lambda, let me zoom in a little bit maybe. T lambda mu nu is equal to minus t mu lambda nu. And t lambda mu nu is equal to minus t lambda nu mu. These two equations follow from 3.23, and the anti-symmetry property of f mu nu equals minus f nu mu of the field strength. They state that t changes sign under the transposition of any two adjacent indices. Any object with however many indices that changes sign under the transposition of every pair of adjacent indices will change sign under the transposition of any two indices. To exchange any two indices, you need an odd number of transpositions of adjacent indices. Do you see why? Yeah, I think I get that. Like, so say we have like just A, B, C, D, E. So say we wanted to swap like A and C. Then what we would need to do is swap A and B. So we have B, A, C, D, E. And because there's one swap there, that's a minus sign. We do another swap, A and C. So that gives us B, C, A, D, E. And then we have to do one last swap to get it to be just the change of A and C right here. So minus C, B, A, D, E. Yeah, so any time we want to change two indices, if like changing adjacent indices gives you a minus sign, then just switching any two indices will give you a minus sign. Okay. Yeah, that makes sense to me. All right. An object that changes sign under the An object that changes sign under the transposition of any two indices is said to be totally antisymmetric. Therefore, T is totally antisymmetric. Since t is totally antisymmetric, it vanishes when any two of its indices take the same value. T is non-vanishing only when each of its three indices takes different value. In such case, I feel like it should be in such a case. Like, this is the, maybe I'm wrong though. I could absolutely see me being wrong. I got a C in English, so yeah, don't take my word for like grammar and stuff. In such case, different orderings of these three fixed values will give t components that can differ by at most a sign. Since we are setting t to 0, these various orderings do not give new conditions. Because we have 4 spacetime coordinates, selecting 3 different indices can only be done in 4 different ways, leaving out a different index each time. Thus, the vanishing of t gives 4 non-trivial equations. These 4 equations are the 3 components of equation 3.1 and equation 3.2. The vanishing of t012, for example, gives us, so this is for t012, we have partial 0 f12 plus partial 1 f20 plus partial 2 f01, which is 1 over c partial bz over partial t plus partial ey over partial x minus partial ex over partial y. Now, and this is what's being set equal to 0. The z component of this is the z component of equation 3.1. The other 3 choices of indices lead to 3 remaining equations. And I'm guessing that's going to be one of the problems after this chapter. How can we describe Maxwell equations 3.3 and 3.4 in our present framework? Since these equations have sources, we must introduce a current 4 vector. So that is j mu, which is equal to c times rho, and then j1, j2, j3. So the time component is the charge density, and the spatial components are the current densities. Yeah. In addition, we raise the indices of the field tensor to obtain the field tensor with upper indices. So f mu nu is equal to eta mu alpha eta nu beta f alpha beta. All right. Equation 3.29, together with the definition of f mu nu with lower indices, gives f mu nu upper indices is equal to eta mu alpha eta nu beta partial alpha a beta minus partial beta a alpha. So eta mu alpha partial alpha times eta nu beta alpha beta, or a beta, minus eta nu beta partial beta eta mu alpha a alpha, where the constancy of the metric components was used to move them across the derivatives. It is customary to apply the rules for raising and lowering indices to partial derivatives. So we write partial mu as eta mu alpha partial alpha. And therefore, as a result, f mu nu with upper indices is just given by partial mu with an upper index, a nu with an upper index, minus partial nu, a mu, again, all upper indices. My handwriting is atrocious. All right. It follows from 3.3 and 3.30 and 3.20 that f mu nu, this time with the upper indices, is, again, we have 0 on the diagonals, but now we have the positive components of the electric field on this side, so Ex, Ey, Ez, negative components here, minus Ex, minus Ey, and minus Ez. And then we have the same magnetic field components, so Bz minus By and Bx, minus Bz, By, minus Bx. All right. Using this equation and the current vector, 3.28, we can encapsulate Maxwell's equations 3.3 and 3.4 as partial F mu nu over partial X nu is equal to 1 over C J mu. In the absence of sources, this equation becomes partial nu F mu nu is equal to 0, which then, when we input the definition of the field strength tensor, gives us partial nu, partial mu, a nu minus partial squared. So this is where we have the two derivative indices contracted with each other, times a mu. Not times a mu, acting on a mu, I should say. And then this equals 0. Yeah, so there's just a partial squared is equal to... So the textbook says partial squared is equal to partial mu, but this isn't like proper notation in my opinion, because these are operators, and so they have to act on something for you to like include them in an equality. So I would say, like, you know, partial squared F is equal to partial mu upper, partial mu lower F. But I'm probably being a little pedantic on that. Like, it gets across the same point, but I do think it's kind of important to, like, you know, keep track of these things when you're trying to build up an intuition of like what these are like as operators. Okay. Equation 3.15 together with equations 3.34 are equivalent to Maxwell's equations in 4 dimensions. We will take these equations to define Maxwell theory in arbitrary dimensions. In d spatial dimensions with Lorentz vector a mu, in d spatial dimensions, the Lorentz vector a mu has components phi and a vector where a vector is a d-dimensional spatial vector. So in 3-dimensional space-time, for example, the matrix F mu nu is a 3x3 antisymmetric matrix, obtained by 3.20 by discarding the last row of the last row and column. So we can write that 3x3 matrix as, again, zeros on the diagonals, minus Ex minus Ey Bz, and maybe I should zoom in so that I can make this legible. Minus Ex minus Ey Bz Ex Ey Bz. And so we can see, just like when we did it without, you know, doing the whole relativistic formalism, we are only left with Ex, Ey, and Bz as the like physical components of our electromagnetic fields. All right. This immediately reproduces the main result of section 3.2. Bx, By, and Ez are to be set to 0. Motivated by 3.33, in arbitrary dimension, we will call F0i the electric field Ei. So Ei is equal to, or defined to be, F0i, which is minus F0i. And the electric field is a spatial vector. Equation 3.18 implies that in any number of dimensions, E vector is equal to minus 1 over c partial a over partial t minus the gradient of phi. That makes sense because, it makes sense to me because there's no reference really to the dimensionality in this expression. That isn't the case for the magnetic field though. Like, remember we saw that like B was defined as the cross product of this del and the vector potential. But this operation here, the cross product of two vectors, is something that's specific to 3 spatial dimensions. And so when we generalize this to higher dimensions, you shouldn't expect to see this exact same equation pop out. All right. Oh, I see what's happening with Mio. Oh, Killnuke, thank you for the follow. I need to fix something with my little spherical friend in the corner here. So he was jumping around every time I talked because I'm using a like PNG tuber program to run him, and so it was still picking up like my mic and pretending that he was talking when he's not. He's just chilling out in the corner over here. So I am going through a textbook on string theory right now called A First Course in String Theory by, let me raise this up a little bit. Yeah, First Course in String Theory by Barton Zweibach. I'm currently on chapter 3, section 3.3, I believe. Right now, I am learning how to do electromagnetism and gravity in higher dimensions. So, the magnetic field is defined with the Fij components of the field strength. So the field strength is this F mu nu object here. Okay. In 4-dimensional space, that's my dog. Hold on a second. I'm gonna go get him and hopefully stop him from barking. All right, sorry about that. My dog can get a little antsy whenever he hears noises outside, so I've got him in my office with me now. All right. So, in 4-dimensional spacetime, Fij is a 3x3 antisymmetric tensor, or matrix. Its 3 independent entries are the components of the magnetic field vector. See 3.33. In dimensions other than 4, the magnetic field is no longer a spatial vector. In 3 spacetime dimensions, the magnetic field is a single component object. In 5 spacetime dimensions, the magnetic field has many entries as a 4x4 antisymmetric matrix, so that is 6 entries. That many components do not fit into a spatial vector. Our next goal is to determine the determination of the electric field produced by a point charge in a space-time with arbitrary but fixed number of spatial dimensions. To this end, we must first learn how to calculate the volumes of higher dimensional spheres. We turn to this subject now. This is actually something that I know a little bit about because my first paper actually involved higher dimensional forces and like bound states particularly, which means I had to, do this kind of analysis for that. So this will be a nice like trip down memory lane for me. All right. So I'm moving on to 3.4, an aside on spheres in higher dimensions. Since we want to work with various numbers of dimensions, we should be precise when speaking about spheres and their volumes. When we speak loosely, we tend to confuse spheres and balls, at least in the precise sense, in which they are defined in mathematics. When you say the volume of a sphere of radius r is 4/3 pi r cubed, you should really be saying that the volume of the 3-ball B3, the 3-dimensional space enclosed by the 2-dimensional sphere S2. Mathematicians are the terminology of like pure mathematics is very stressful. All right. In 3-dimensional space R3, as it's called, with coordinates x1, x2, and x3, we write the 3-ball as the region defined by B3 of R is defined by x1 squared plus x2 squared plus x3 squared is less than or equal to r squared. If you like, you can also think of this as like x, y, and z. The x1, x2, x3 thing just is a useful notation when we're talking about higher dimensions, because it's much easier to, you know, add on an x4 than to, say, like, come up with a new letter after z. All right. The region enclosed by the 2-sphere S2 of R, which is x1 squared plus x2 squared plus x3 squared, is equal to r squared. So not like less than or equal to, it's just equal to. So a sphere is specifically like the shell of what we would consider a sphere, whereas the ball is when you consider, like, you know, the surface and all of the points that it encloses. The superscripts in B or S denote the dimensionality of the space in question. When we drop the explicit argument r, we mean that r is equal to 1. Lower dimensional examples are also familiar. B2 is a two-dimensional disk, the region enclosed in R2 by the one-dimensional unit radius circle S1. Oh yeah, so if anyone isn't like familiar, a circle is just a one-dimensional like sphere. So we consider like all the points on a sphere, that's like a two-dimensional surface. If we were to consider the same concept but on one dimension, what we get is a circle. All right. In arbitrary dimensions, we define balls and spheres as subspaces of RD. So BD of R is x1 squared plus x2 squared plus ... all the way until xd squared is less than or equal to r squared. And the sphere SD minus 1 of R is just the same thing, but again with an equality rather than an less than or equal sign. So x1 squared plus x2 squared plus ... plus xd squared is equal to r squared. I'm going to reset. Cal's looking a little stiff, so I'm going to reset the settings that I had just changed. Yeah, see? Now you can move around more. Hello! Okay, cool. All right. One last piece of terminology. To avoid confusion, we will always speak of volumes. If a space is one-dimensional, we take the volume to mean length. If a space is two-dimensional, we take the volume to mean area. All higher dimensional spaces have just volumes. The volumes of one- and two-dimensional spheres are, so the volume of S1R is equal to 2 pi r. So what this is just a mathematical way of saying the volume of a circle of radius r. And because we mean length, what we're talking about here is circumference. So the circumference of a circle with radius r is 2 pi r. Similarly, the volume of S2r is 4 pi r squared. And so we're saying the volume of the two-dimensional sphere R, what we really mean is the surface area of the two-dimensional sphere of radius R. And these are the, typical expressions that you would use for that. Unless you have worked out other spheres before, you probably do not know what the volume of S3 is. Since volume has units of length to the power of the spacetime dimension, the volume of a sphere of radius R is related to the volume of a sphere of the is related to the volume of a sphere of unit radius by, so the volume of SD minus 1 of R is equal to R d minus 1 times the volume of S d minus 1. So, and again, because we've dropped the argument here, we just mean the unit sphere. Since radius depends on since the radius depends on the volume, since the radius dependence of the volume is easily recovered, it suffices to record the volumes of unit spheres. So the volume of S1 is equal to 2 pi. The volume of S2 is equal to 4 pi. Let us now begin our calculation with the volume of the sphere d minus 1. For this purpose, consider RD with coordinates x1, x2, all the way to xd, and let r be the radial coordinate. And this is a lowercase r this time, so r squared is equal to x1 squared plus x2 squared plus ... all the way up to xd squared. We will find the desired volume by evaluating in two different ways the following integral. So ID is equal to the integral over RD of dx1, dx2, all the way to dxd of e to the minus r squared. First, we proceed directly using 3.46, which is this equation right here. Okay. In the exponential factor, the integral becomes a product of d Gaussian integrals. So ID becomes the product from I equals 1 to d of the integral from negative infinity to infinity of dxi e to the minus xi squared, which is just the square root of pi to the power of d, which is just pi to the d over 2, because the square root is like just raising something to the power of 1/2. Now we proceed indirectly. We do the integral by breaking RD into thin spherical shells. Since the space is of constant r is the spheres SD1 of r, then the volume of the shell lying between r and r plus dr equals the volume of s to the d minus 1, so the d minus 1 dimensional sphere of r times dr. So therefore, ID is equal to 0 to infinity dr times the volume of sd minus 1 of r times e to the minus r squared. And so we pull out the units volume, because we said before that, like, the volume of s to the d minus 1 of r is just equal to r to the d minus 1 of the volume of the unit sphere of the same dimensionality. So we get the volume of s to the d minus 1 times the integral from 0 to infinity dr r to the d minus 1 e to the minus r squared. This is going to be 1/2 the volume of s to the d minus 1 times the integral of 0 to infinity dt e to the minus t times t to the d over 2 minus 1. And I can already predict where this is going. This is a special kind of integral called a gamma function. And it's actually related to factorials, believe it or not. But here we're going to get things weird because obviously you can't have factorials with non-integer arguments. So you can take like the factorial of like 3.5. But you can do a gamma function with like an argument of 3.5. So that's why gamma functions are useful. Okay. And so they've made use of 3.44 in the final step. We changed the variable of integration from from r to t, which is equal to r squared. The last integral on the right-hand side can be expressed in terms of the gamma function, a very useful special function. For positive x, the gamma function is, so we have gamma of x is equal to the integral from 0 to infinity dt e to the minus t to the x minus 1, where x is greater than 0. Unless x greater than 0, the integral does not converge near t equals 0. Okay, yeah. With this definition, equation 3.49 becomes ID is equal to 1/2 times the volume of s d minus 1 gamma d over 2. Comparing with earlier evaluation of 3.48, we get our final result, that the volume of the sphere of dimension d minus 1, the unit sphere of dimension d minus 1, is equal to 2 pi to the d over 2 divided by gamma d over 2. It now remains to calculate the value of d over 2. Since d is an integer, we must determine the values of the gamma function for both integer and half-integer arguments. To find gamma of 1/2, we use the definition gamma of 1/2 is equal to the integral from 0 to infinity dt of e to the minus t t to the negative 1/2, which is 2 times the integral from 0 to infinity dt, or no, du, I should say, because we're doing a little change of variables here, e to the minus u squared, which is a Gaussian integral, so we have just the square root of pi. Similarly, gamma of 1 is equal to the integral from 0 to infinity of dt e to the minus t, which is just 1. For larger arguments, the calculation of the gamma function is simplified using the recursion relation. To obtain this relation, begin with gamma of x plus 1. And so this is equal to the integral from 0 to infinity dt e to the minus t to the x. And again, x must be greater than 0. This can be rewritten as minus the integral from 0 to infinity dt of the derivative, so d by dt, e to the minus t to the x, which is then minus the integral from 0 to infinity dt times d by dt of e to the minus t tx minus x e to the minus t t to the x minus 1. Now the boundary term will vanish for x greater than 0. That's this term right here. And so we're only going to be left with x times the integral from 0 to infinity of dt e to the minus t t to the x minus 1, which should look familiar because this is just gamma of x. Or yeah, here, let me skip a line. So we have the relationship that gamma of x plus 1 is equal to x times gamma of x. So this is where we get the like analogy to the factorial. You know, like n factorial is equal to like n times n minus 1 times blah blah blah, all the way down to 1. Okay. For integer arguments, the gamma function is related to the so that's what is related to the factorial. So yeah, in fact, I think it's gamma of n is equal to n minus 1 factorial. So that's for n, which is an integer. So we have n belonging to the set of integers, which is denoted with this weird z. Okay. And we have to recall that 0 factorial is equal to 1. So now we can test our formula 3.52 in the familiar case. So the volume of S1 is equal to the volume of S2 minus 1. So we have here 2 to the pi, or 2 times pi to the 2 over 2 divided by gamma of 2 over 2. So that's 2 pi divided by gamma of 1. Gamma of 1 is 0 factorial, which we just said was 1. So this is just 2 pi, like we got before. Now let's look at the volume of the 2 sphere, S2. So we have volume of S3 minus 1. So we have 2 pi to the 3 halves divided by gamma of 3 halves, which is 4 pi. Exactly what we got before. In agreement with the known values. So for the less familiar S3, we find that the volume of S3 is volume of S4 minus 1, which is 2 pi squared divided by gamma of 2, which is just 2 pi squared. All right, and that's the end of the discussion on oh my god, higher dimensional spheres and their like volumes. Okay, so now let's move on to section 3.5, electric fields in higher dimensions. In this section, we will calculate the electric field due to a point charge in a world with d spatial dimensions, where d could be 3, in which case the answer is familiar, or less than 3, but we are particularly interested in d greater than 3. To do this calculation, we will use the general version of Maxwell's equations, appropriate for an arbitrary number of spatial dimensions. As you may imagine, the electric field of a point charge is radial. Our calculation will give the radial dependence and the normalization of the electric field. With minor modifications, this result will also inform us of the gravitational fields of point particles in d spatial dimensions. Sorry. Lots of talking. Our computation is based on the 0th component of equation 3.34. So we have partial f 0I divided by partial xi is equal to rho. Since f 0I is equal to ei, This is just Gauss's law. So the divergence of the electric field is equal to the charge density. Gauss's law is valid in all dimensions. That's kind of lucky. It's definitely not the case for like the magnetic field ones. Yeah, I was coughing a lot earlier today, and I think all this talking is starting to strain my voice, but I want to keep going. I like these string theory streams. Gauss's law is valid in all dimensions. Equation 3.63 can be used to determine the electric field of a point charge. Let us first review how this is done in the familiar setting of three spatial dimensions. Consider a point charge Q and two sphere S2 of R of radius R centered on the charge, and the three ball B3 of R whose boundary is the two sphere. We integrate both sides of the equation over the three ball to find, okay, so the integral over the three ball of the derivative, or like the d volume dot E is equal to B3 d volume. Usually you'll see this just like written as like D capital V, but this is what the textbook's designed to use, so I'll keep using that too. Okay. We use the divergence theorem on the left-hand side and note that the volume integral on the right-hand side gives the total charge. So, basically the divergence theorem says that the integral, like the volume integral, of the divergence of some field, some vector field, is just given by the now surface area integral of the electric fields, or like that vector field like dotted into your surface area. In other words, like the flux. Okay. So in this case we have the integral over the two sphere of radius R of E dot dA is equal to the charge Q, because we're just taking this charge density and integrating over the entire volume. So basically it's just taking like all of the charge and adding it together is essentially what's happening with that. It's a little bit more complicated, but that's like the gist of it. Like conceptually, you're just taking all the charge enclosed by the sphere and adding it together. All right. Since the magnitude E of R of the electric field is constant over the two sphere, we get that the volume of S2 of R times E of R is equal to Q. And the volume of the two sphere is just 4 pi R squared, so E of R is equal to Q over 4 pi R squared. If you're taking E&M and you're watching this, you'll notice something's a little fishy. There's no epsilon naught that's missing. It's because we're using particular units called Heaviside-Lorentz units rather than the standard, like the SI units. The System International, I think is what SI stands for. Yeah. But we're using special units in which epsilon's naught is just 1, I believe. All right. Since okay. Yeah. This is the familiar result for the electric field of a point charge in 3 spatial dimensions. The electric field magnitude falls off like 1 over R squared. For dimensions higher than 3, the starting point 3.63 is good, so we must ask if the divergence theorem also holds. It turns out that it does. We will first state the theorem in d spatial dimensions, and then we will give some justification for it. Consider a d-dimensional subspace VD, so a d-dimensional subspace VD of RD. and let partial VD denote the boundary of VD. Okay. Moreover, let E be a vector field in RD. The divergence theorem states that the integral of over VD, or say the volume integral over VD of the divergence of E is equal to the flux of E across the surface partial VD, which is then just equal to the integral partial VD of E dot dV. The last right-hand side requires some explanation. At any point on partial VD, the space partial VD is locally approximated by the d-1 dimensional tangent hyperplane. So if we're thinking of like a sphere, and maybe I'll do it like this. We can consider like at every point like a little plane that is tangent to it. And I didn't draw that in the right perspective. Say like we consider a plane that is touching it at just that point. That's like the tangent plane, and so we want to consider the flux of E through that tangent plane. For a small piece of dVd around this point, the associated vector dv, so this right here, like little v, is a vector orthogonal to the hyperplane pointing out of the volume, with a magnitude equal to the volume of the small piece under consideration. Note that this explanation is in accord with your experience in R3, where dv corresponds to the area vector element dA. Let us justify the divergence theorem for this case of 4 spatial dimensions, following a strategy used in elementary textbooks. It suffices to prove that the divergence theorem for a small hypercube, the result for general subspaces follows by breaking such spaces into many small hypercubes. Because it is not easy to imagine a 4-dimensional hypercube, we will be using a 3-dimensional picture with 4-dimensional labels. Figure 3.1. We use Cartesian coordinates x, y, z, and w. Consider a cube whose faces lie on the hyperplane selected by the condition that one of the coordinates is constant. Let one face of the cube let one face of the cube and the face opposite to it lie on hyperplanes of constant x and constant x plus dx, respectively. The outgoing normal vectors are ex for the face at x equals or at x plus dx, and minus ex for the face at x. Lots of x's. The volume of each of these two faces equals dy, dz, dw, where dy, dz, and dw together with dx are the lengths of the edges of the cube. For an arbitrary electric field E of x, y, z, w, only the x component contributes to the flux through these two faces. The contribution is Ex of x plus dx, so x plus dx, comma, y, z, w, and we have a bracket around here, minus ex of x, y, z, w, and bracket dy, dz, dw. Right? So this is approximately partial e over, or partial ex over partial x, dx, dy, dz, dw. And we can see that this right here, if we consider all of the components, would just be the like divergence. if we added them together. So analogous expressions hold for the fluxes across the three other pairs of faces. The total net flux from the little cubes is just, so the flux of E, sometimes that'll be denoted as like phi sub E, is equal to partial E sub x over partial x plus partial EY by partial y plus partial EZ over partial z, and then plus partial EW over partial W. Can't forget the last one. And then dx, dy, dz, dw, which is just the divergence of E and then times the differential volume element. This result is precisely the divergence theorem 3.68 applied to infinitesimal hypercube. This is what we wanted to show. We can now return to the computation of the electric field due to the point charge in a world with d spatial dimensions. Consider a point charge q, the sphere sd minus 1 of r, and radius r centered on the charge. This is the sphere that surrounds the charge. The ball B, whose boundary is sd minus 1 of r, and the ball B, whose boundary is sd minus 1. Again, we integrate both sides of the equation over the ball B. So here we have the integral BD times the volume integral of the divergence of E is equal to the integral over BD d volume rho. So this gives us the flux of E across sd minus 1 of r is equal to the charge enclosed. The volume integral on the right side gives the total charge, and the divergence theorem 3.68 relates the left-hand side to the flux integral. Yeah. All right. The flux equals the magnitude of the electric field times the volume sd minus 1 of r. So we have E of r times the volume of s d minus 1 of r is equal to q. And then making use of like the volume expressions that we found before, we find that the electric field as a function of the radius away from the point charge is going to be gamma d over 2 divided by 2 pi d over 2 q over r to the d minus 1. This is actually this is the expression that I found for, the 1 over, or the specifically the Coulomb potential, which, Coulomb. Yeah, so this is a generalization of the Coulomb potential. Basically, like if you have a infinite range force in higher dimensions, this is what you'll get. I also, in my research, did it for other cases, not just for the Coulomb interaction. And so you can add like on different functional forms to it. Specifically, I focused also on Yukawa interactions. So that's where like you have like, that in 3 dimensions, you have like 1 over r squared, but you also have a like exponential decay of your potential. And I generalized that also to higher dimensions. But the interesting cases were when you took either like, a Coulomb potential and a Yukawa potential that like were opposing each other. So like if one of them was an attractive potential, the other was repulsive. Or if you took like 2 Yukawa potentials that had different effective ranges, what you end up finding is that you can have bound states in basically any dimension that you want, provided that you like fine tune your parameters of your potentials properly. So it's pretty neat. Okay. This is the value of the electric field for a point charge in a world with d spatial dimensions. For d equals 3, we recover the inverse square dependence of the electric field. In higher dimensions, the electric field falls off faster at large distances. For each additional spatial dimension, we get an additional factor of 1 over r in the radial dependence of the electric field. Okay. The electrostatic potential phi is also of interest. For the time, for time-independent fields, 3.38 gives E is equal to minus the gradient of phi. This equation, together with Gauss's law, provides the Poisson equation. So del squared phi is equal to minus rho, the charge density, which can be used to calculate the potential due to a charge distribution. The two equations above hold in all dimensions, using, of course, the appropriate definitions of the gradient and the Laplacian. Yeah, so this right here is the gradient operator. This one with the squared is the Laplacian. And actually, if you set like rho equal to 0 in this case, so like if we do this, this becomes not Poisson's equation, but Laplace's equation. But right now, I think we're going to be talking about the Poisson equation. All right, I think we're going on to 3.6 now, gravitation and Planck's length. Einstein's theory of general relativity is a theory of gravitation. In this very elegant theory, the dynamical variables encode the geometry of space-time. When gravitational fields are sufficiently weak and velocities are small, Newtonian gravitation is accurate enough, and one need not work out the more complex machinery of general relativity. We can use Newtonian gravity to understand the definition of Planck's length in various dimensions and its relation to the gravitational constant. These are interesting issues that we will explain here and in the rest of the present chapter. Nevertheless, when gravitation emerges in string theory, it does so in the language of Einstein's theory of general relativity. To be able to recognize the appearance of gravity among the quantum vibrations of the relativistic string, you need a little familiarity with the language of general relativity. Here, you will take a first look at the concepts involved in this remarkable theory. Most physicists do not expect general relativity to hold at truly small distances, nor for extremely large gravitational fields. This... Sorry, I should have muted. This is the realm where string theory and the first series candidate for a quantum theory of gravitation is necessary. General relativity is the large distance weak gravity limit of string theory. String theory modifies general relativity. It must do so to make it consistent with quantum mechanics. The conceptual framework which underlies the modification is not clear yet. It will no doubt emerge as we understand string theory better in the years to come. The space-time of special relativity, Minkowski space-time, is the arena of physics and the absence of gravitational fields. The geometrical properties of Minkowski spacetime are encoded by the metric formula, which gives the invariant interval separating two nearby events. So that was from last time we saw minus ds squared is equal to eta mu nu dx mu dx nu. Here, the Minkowski metric eta mu nu is a constant metric represented by the matrix with entries minus 1, 1, 1, and so on, along the diagonal. Minkowski space is said to be a flat space. In the presence of a gravitational field, the metric becomes dynamical. We then write minus ds squared is equal to g mu nu of x dx mu dx nu, where the constant eta mu nu is replaced by the metric g mu nu of x. If there is a gravitational field, the metric is in general a non-trivial function of the spacetime coordinates. The metric g mu nu is defined to be symmetric. So g mu nu of x is equal to g nu mu of x. All right. It is also customary to define g upper mu nu, the inverse metric of g mu nu, using g mu alpha of x, g alpha nu of x is equal to delta mu nu, where we have, again, this delta is the Kronecker delta that we saw before. For many physical phenomena, gravity is very weak, and the metric g mu nu can be chosen to be very close to Minkowski metric eta mu nu. We then write g mu nu of x is equal to eta. Oop, I should have lower indices here. So we're talking about the metric, not the inverse metric. Mu nu plus h mu nu of x. Oh, gosh, Cal is really jumping around everywhere today. Here, h mu nu is something that's often called the metric fluctuation. Yeah, so here we view h mu nu of x as a small fluctuation around Minkowski metric. Yeah, so it's called the metric fluctuation. This is actually what we use to describe like gravitational waves, because they're just small fluctuations around flat space-time. Like, so if we have like this propagating in like a wave pattern. Okay. The expansion is done, for example, to study gravitational waves. Oh, that's what I just said. Yeah. Those waves represent small ripples on the top of the Minkowski metric. Einstein's equations for the gravitational field are written in terms of space-time metric g mu nu of x. These equations imply that matter or energy sources curve the space-time manifold. For weak gravitational fields, Einstein's equations can be expanded in powers of h mu nu using 3.81. In the absence of sources, the resulting linearized equation for h mu nu is partial squared h mu nu. So this is a generalization to higher dimensions of the Laplacian that we saw before, like the del squared. When we have a partial, it means that we're not like specifying that we're talking about 3 spatial dimensions, and in fact we're also including time in it in this case, because like we can see that we're dealing with like Lorentz indices. Minus partial alpha partial mu h nu alpha plus partial nu h mu alpha, and then lastly plus partial mu partial nu h is equal to 0. So here they have the inverse metric fluctuation. The h mu nu is defined to be, or I guess it's not the inverse metric fluctuation. Yeah, I don't think so, because it's being raised with, it gets complicated when you're talking about general relativity. Mu alpha eta nu beta h alpha beta, and they define h, so without any indices, as eta mu nu h mu nu. So the reason that they're defining these not with the full metric like g mu nu or g mu alpha g nu beta is because we're typically going to be taking the limit in which h is small, and so we neglect anything that is like of order h squared. And so since we already have this h here, we just get rid of h in this part of it, leaving only the etas. This is this is called the weak field limit. Okay. Equation 3.82 is the gravitational analog of equation 3.35, which describes Maxwell fields in the absence of sources. While 3.35 is exact, 3.82 is only valid for weak gravitational fields. It is the linear approximation of a nonlinear equation that includes additional terms, quadratic and higher order in H. The analogy with electromagnetism extends to the existence of gauge transformations. Einstein's gravity has gauge transformations. These arise from the use of different systems of coordinates. They arise because the use of different systems of coordinates yields equivalent descriptions of gravitational physics. There we go. Words. The words are wordsing now. In learning string theory in this book, you will get to appreciate the freedom to choose coordinates on surfaces generated by moving strings. In general relativity, an infinitesimal change of coordinates, x mu prime, is equal to x mu plus epsilon mu of x, can be viewed as an infinitesimal change of the metric g mu nu, and using 3.81 as an infinitesimal change in the fluctuation of the field, one can show that the change is given by... Oh, something's going on with my PDF viewer. Okay, there we go. Delta h mu nu is equal to delta 0 h mu nu plus order epsilon h, with delta 0 h mu nu being equal to partial mu epsilon nu plus partial nu epsilon mu. As indicated above, the infinitesimal change delta h mu nu is given by delta 0 h mu nu plus corrections. Written as epsilon dot order h, that are linear in epsilon and linear in the fluctuation h itself. The invariance of the full nonlinear equation of motion under the gauge transformations delta h mu nu requires the invariance of the linearized equation of motion 3.82 under delta 0 h mu nu. Indeed, when we vary the h's in 3.82 using delta 0 h mu nu, we get terms linear in epsilon but without an h. These terms must cancel out completely because all other variations will contain at least one field h. This is clear for the variations of 3.82 using the terms represented by epsilon dot order h, and for all variations of terms quadratic or higher order in h in the complete equation of motion. We will check the invariance of 3.82 under the transformation of delta 0 h mu nu in chapter 10. In Maxwell theory, the gauge parameter has no indices, but in general relativity, the gauge parameter is a vector index. As we mentioned before, Newtonian gravitation emerges from general relativity in the approximation of weak gravitational fields and motion with small velocities. For many purposes, Newtonian gravity suffices. Starting now, for the rest of the chapter, we will use Newtonian gravity to understand the definition of Planck's length in various dimensions, to investigate how gravitational constants behave when some spatial dimensions are curled up. The results we will obtain hold also in the full theory of general relativity. Newton's laws of gravitation in 4 dimensions states that the force of attraction between two masses m1 and m2 separated by a distance r is given by F, so it has a superscript 4, is equal to G m1 m2 over r squared, where G denotes the 4-dimensional Newton constant. It follows that the units of the gravitational constant G are, so we have G, the units of G are equal to the units of force times length squared over mass squared, which is mass times length over time squared times length squared over mass squared, which is then length cubed over mass times time squared. The numerical value of the constant g is determined experimentally to be g is equal to 6.674 times 10 to the negative 11 meters cubed per kilogram second squared. Since c is equal to L over t and h bar, so the units of c are length over time and the units of h bar are m L squared over t. Hold on, let me think about that. Sorry, I was thinking like natural units. In natural units, h bar is dimensionless. But we're not using natural units right now. So the units of h bar are mass times length squared over time. The three fundamental constants g, c, and h bar can be written as, so we have g written there, c is equal to 2.998 times 10 to the 8 meters per second, and h bar is equal to 1.055 times 10 to the negative 34 kilograms meters squared per second. In the study of gravitation, it is sometimes convenient to use Planckian system of units. Since we have three basic units, those of length, time, and mass, we can find new units of length, time, and mass such that the three fundamental constants g, c, and h take on the numerical value of 1 in those units. These units are called Planck length. The units are called the Planck length, the Planck time, and the Planck mass. In those units, g is equal to 1 Planck length cubed divided by the Planck mass times the Planck time squared. C is equal to 1 times the Planck length over the Planck time. And h bar is equal to 1 times the Planck mass times the Planck length squared divided by the Planck time. Without additional numerical constants, as opposed to equation 3.88, the above equation allows us to solve for LP, TP, and MP in terms of G, C, and H bar. One readily finds that LP is equal to the square root of G H bar over C cubed, which is equal to 1.616 times 10 to the negative 33 centimeters. TP, which is the Planck length over C. So we have the square root of G H bar over C to the fifth. Gives a Planck time of 5.391 times 10 to the negative 44 seconds. And the Planck mass, which is the square root of H bar C over G, is given by 2.176 times 10 to the negative 5 grams. These numbers represent scales at which relativistic quantum gravity effects can be important. Indeed, the Planck length is an extremely small length. The Planck time is an incredibly short time, the time that it takes light to travel the Planck length. While Einstein's gravity can be used down to relatively small distances and back to relatively early times in history of the universe, a quantum gravity theory such as string theory is needed to study gravity at distances of the order of the Planck length, or to investigate the universe when it was Planck time old. There is an equivalent way to characterize the Planck length. LP is the unique length that can be constructed using only powers of G, C, and H bar. One thus sets LP equal to G to the alpha times C to the beta times H bar to the gamma, and fixes these constants alpha, beta, and gamma so that the right hand side has units of length. Okay. It may appear that MP is not a very large mass, but it is in fact a spectacularly large mass from the viewpoint of elementary particle physics. The mass MP is roughly 10 to the 19 times larger than the mass of the proton. If the fundamental theory of nature is based on the basic constants g, c, and h bar, then it is a great mystery why the masses of elementary particles are so much smaller than the obvious mass MP that can be built from the basic constants. This puzzle is usually called the hierarchy problem. For an additional perspective on the Planck mass, consider the following question. What should the mass m of the proton what should be the mass m of the proton so that the gravitational force between two protons cancels out the electric repulsion between them? Equating the magnitudes of the electric and gravitational forces, we get g m over r squared is equal to e squared over 4 pi r squared, which gives us g m squared is equal to, I missed the squared here. G m squared is equal to e squared over 4 pi. It is convenient to divide both sides of the equation by h bar over c to find g m squared over h bar c equals e squared over 4 pi h bar c, which is approximately 1 over 137. This is a very important value in electrodynamics. This is called the fine structure constant. Sometimes you'll also see it referred to as alpha. There is a really big delay between what's being written on my tablet and what's showing up on OBS. Oh well. Okay. And so then we get that m squared over mp squared is approximately 1 over 137, where use was made of 3.92. We thus find that m is approximately 1/12 of the Planck mass, or about 1/10, I guess is what they're saying, of the Planck mass. The dimensionless ratio e squared over 4 pi h bar c is called the fine structure constant. That's what I said. It is evaluated above using the Heaviside-Lorentz definition of the electric charge, where E is equal to the square root of 4 pi times 4.8 times 10 to the negative 10 ESU. All right. And now we have 3.7 gravitational potentials. My voice is killing me. I think I might call it here for the night. All right. Thank you again, Killnuke, for the follow. I really appreciate it. And I'll see everyone next time.